Welcome to the Peacademia course on the basics of semiconductors. This lecture covers the Triac and GTO. Let's start. By the time you finish this lesson, you will learn the Triac structure, Triac model, gate turn-off thyristor or GTO, and the conditions to turn off a GTO through the gate. In the last two lectures, I introduced the thyristor and went through its details. Through studying the thyristor, we learned how it operates and how it is modeled. We learned that a thyristor is a controlled rectifying device that conducts in one direction. In some applications, such as light dimmers, it is required to have a bidirectional thyristor. This can be simply achieved by having two anti-parallel thyristors whose gates are connected together. In this case, it is difficult to distinguish the anode and cathode pins. Therefore, instead of calling them anode and cathode, we call them main terminal 1, MT1, and main terminal 2, MT2. This circuit model can be represented by this symbol. This new device is called triode AC switch or triac. Another way to make a triac is to structure semiconductor layers properly. Let's see what the triac structure looks like. Here I have the main terminal MT1 and MT2. The terminal MT1 is connected to an N+ layer and a P layer. In the bottom, the main terminal 2 is connected to a P layer and an N+ layer. And an N- layer, which is called the base, is sandwiched between these two. The gate is jointly connected to the top N+ and P semiconductor layers. As far as I'm concerned, in this lecture, we do not need to go into every single detail of the triac operation. A triac is made of two anti-parallel thyristors, and since I discussed the thyristor in detail before, you can use the same concept to understand how the triac works. The IV diagram of the triac is given here. It is evidence that the triac conducts in both directions, and depending on the gate current, the device can turn on under a smaller voltage drop. Similar to a thyristor, when the triac is triggered, it does not stop conducting unless the current passing through the device becomes smaller than the holding current. To guarantee robust switching actions, di over dt and dv over dt of a triac must be limited, otherwise during the voltage or current transition, the device can remain in the on state and does not wait for the gate signal. To give you an idea how much would be the di dt and dv dt, we can think of 10 ampere per microsecond and 100 volt per microsecond. Because of this reason, if we are dealing with a power conversion application with more than 50 ampere, it is recommended to use two discrete thyristors connected anti-parallel. In some applications, you may want to have a thyristor that not only turns on by a gate signal, but also turns off by using the gate. To provide this feature in 1980s, the gate turn-off thyristor or GTO was introduced. However, after the introduction of the IGBT, GTOs are these days of less use. In fact, GTOs are used in the range of power that cannot be reached by IGBTs. A typical power range in which GTOs are used is 6 kA, 6 kV. If you are not familiar with IGBT, don't worry, stay patient. I'll introduce the device in the following lectures. The structure of a gate turn-off thyristor looks like this. Starting from the bottom, we have the anode terminal, then a P-type semiconductor, then an N- semiconductor. On the top of it, a P-type semiconductor and two small N+ regions. The N+ regions are connected together and they form the cathode terminal. The gate is connected to the top of the P semiconductor. By carefully looking at this structure, you'll soon notice that It is very similar to the thyristor structure, and the main difference is in the concentration of dopants in each semiconductor layer. Let's look at the IV diagram of the GTO to gain a better understanding about its electrical behavior. Under the reverse blocking mode, the GTO behavior is the same as the thyristor. Under the forward blocking mode, the turn-on behavior of the GTO is again the same as that of the thyristor, so not too much to add. What I am mostly concerned here is to see that how the GTO is turned off when a negative current gate pulse is given to the GTO. If I apply a voltage to the gate that causes current draw from the gate, and if that current is large enough, the turn-off transition happens. First, the voltage over the GTO increases, but the forward current remains almost intact. This is because of the recombination time of the accumulated charge carriers inverted the top P semiconductor. What happens next is that the current drops and finally gets smaller than the holding current. This turns off the GTO. The question that we have to ask here is how much current do I have to draw from the gate to turn off the GTO? In fact, this is a very, very good question. The answer determines where we can use this device. To address this question, we need to take a look at the BJT model of the GTO. Surprisingly, it is the same as that of the thyristor. If you remember the thyristor lecture, you notice the equation we obtained to calculate the anode current. That is given here. The current through the base of Q2 equals the sum of IG and IC1. Consider that the GTO is on, therefore IC1 has a positive value. To turn off the GTO, the current going through the base of Q2 must become 0. Since IB2 equals IC1 plus IG, to get a base current of 0, IG must be equal to minus IC1. First, this condition looks normal. However, when we look at the relationship between the anode current and IC1, we soon notice that what a big problem we are going to face. IC1 equals alpha 1 times IA. Alpha 1 equals beta 1 minus 1 divided by beta 1. So, alpha 1 is always smaller than 1. If beta 1 is a large quantity, let's say 100, alpha 1 is very close to 1, and we can assume it is 1. So if the forward current or IA is 100 ampere, when the GTO is in the on state, to turn it off, the gate current must be minus 100 ampere, which is a lot. What kind of a gate driver can provide that much of current? How much would be the gate driver loss? As a result, the GTO is designed to have smaller values of beta or alpha. Even if beta is 2, which is a very small current gain, alpha 1 becomes 0.5. So if I again consider that IA equals 100 ampere, the gate current must be minus 50 ampere to turn off the GTO. So what we can conclude from this discussion is that GTO is not a proper device for high power applications because of the current gain issues. In this lecture, I discussed the Triac structure, Triac model, gate turn-off thyristor or GTO, and the conditions to turn off a GTO through the gate. In the next lecture, I will cover MOSFETs. Thanks for joining this lecture of Peacademia.